Welcome to The Explainer. Today we're going to put on our detective hats because we are cracking the case of systems of three linear equations. Yeah, it's a classic algebraic mystery, and you and we're going to solve it together.
All right, so let's just dive right in. Now, I know this might look a little intimidating at first glance, but really, I want you to think of it like a puzzle. We've got three clues, those are our equations, and three suspects that we need to pin down, x, y, and z.
So what's the catch? Well, our solution can't just work for one or two of the clues. Nope, our job as the lead detective here is to find that one single set of values for x, y, and z that makes every single one of these equations true, all at the same time. To pull that off, we need a solid, systematic approach. We have to become algebraic detectives, right? We just follow the evidence where it leads. So, come on, let's grab our toolkit and get started. Okay, first things first. Any good detective knows you gotta organize your evidence or you're just gonna get lost. So that's what we'll do. We're gonna label our three equations, our clues, as A, B, and C. This is gonna help us keep everything straight as the case unfolds.
All right, so what's the big strategy here? The real secret to solving a three-suspect mystery is to, well, make it easier. We're going to simplify it down to a two-suspect mystery, something we already know how to handle. The goal is to systematically eliminate one of the variables, leaving us with a much simpler system to crack.
And that brings us to our official four-step toolkit. Think of this as the standard procedure for cracking these kinds of cases. It's a super reliable method. If you just follow it carefully, it's going to lead you to the solution every single time.
So here's the game plan. It's called the elimination method. We're going to pair up two equations and eliminate one of our suspects. Then we do it again with a different pair of equations. That'll leave us with a way simpler case to solve, and from there, we can work backwards to identify all our variables.
Okay, that's enough theory. It's time to put our toolkit to the test, right? Let's apply this four-step method to our original puzzle and see if we can just crack this thing wide open.
All right, step one. We're going to pick equations A and B. And if you look closely, equation A has a minus z and B has a plus z. They're perfect opposites. So when we just add the two equations together, poof, the z variable is gone. It just vanishes. And that leaves us with a brand new equation, which we're going to label D. This, my friend, is our first major break in the case. We've done it. We've reduced a piece of this mystery down to just two variables, x and y.
Okay, on to step two. We need to pick a different pair of equations. Let's go with A and C this time. And here's the really critical part, so listen up. We have to eliminate the exact same variable, z. Now, to make that happen here, we'll need to multiply all of equation A by 2. That'll give us a negative 2z, which will perfectly cancel out the positive 2z in equation C. And boom, there we have it. We add those together, and we get our second crucial clue. We'll call this one equation E. So now we have another piece of the puzzle, and again, it's just got x and y in it.
So, just take a step back and look at what we've done. We've got our new clues D and E, and when you put them together, we've successfully turned this complicated three-variable problem into a simple two-variable system. And this is a case we definitely know how to solve.
All right, time for step 3, solving this new system. So if we look at D and E, it looks like we can eliminate x pretty easily this time. All we have to do is multiply equation D by -1. Then when we add it to E, you can see the x terms are just going to cancel each other right out.
And just like that, there it is. We've unmasked our first suspect. We now know for sure that y is equal to 1.
Once you identify one suspect, the whole case just starts to unravel pretty quickly. So now we can take that value, y equals 1, and plug it back into one of our simpler clues. Let's use equation D. That'll help us find the identity of our next suspect. A little bit of simple algebra, and boom, our second variable is solved. X equals 2. That's 2 down, 1 to go. And now for the final step, step 4. We take both values we found, x equals 2 and y equals 1, and we substitute them back into any one of our original three equations. It doesn't matter which one you pick. Let's just use equation B. We plug in the numbers, do the math, and there it is. The final unknown is revealed. Z is equal to 0. Case closed. So, the one single solution that makes all three of our original clues true is the ordered triple 2, 1, 0.
And just so you know, in the official language of math, when a system has one unique solution like this, it's called a consistent and independent system.
But you know, not every mystery has such a neat and tidy solution. Sometimes the clues just seem to contradict each other and the case goes cold. Now here's a cool way to think about it. Geometrically, you can picture each of these equations as a flat plane in three-dimensional space. That one solution we found, well, that's the single point where all three of those planes cross. But sometimes those planes, they just don't cooperate.
So what happens if, right in the middle of your detective work, all your variables just disappear, and you're left with a statement that's just obviously false, something impossible like 0 equals 7? Well, that's a huge red flag in your investigation.
This is what we call a contradiction. It basically means the clues you were given just don't work together. They're incompatible. Thinking about those planes again, it's like they never all cross at the same point. Maybe two of them are parallel, or they intersect in a way that never meets up. The bottom line is there is no solution, and the system is officially called inconsistent.
But okay, there's another weird possibility. What if your variables disappear again, but this time you're left with a statement that is always true? Something like 0 equals 0.
This kind of twist ending means your clues aren't contradicting each other, they're just redundant. It's like one of the clues is just a clever disguise for another one. And what this tells you is that there isn't just one right answer. There are actually an infinite number of solutions. Visually, it means the three planes are all intersecting along a single line, or maybe they're all just the exact same plane stacked on top of each other. We call this a consistent and dependent system.
So when you get right down to it, every one of these investigations you take on is going to lead to one of three possible endings.
And this table here, it just summarizes the whole shebang. You'll either find that one unique solution, that's our consistent and independent system, where the planes meet at a single point. Or you'll hit a dead end with a contradiction, which tells you there's no solution. That's an inconsistent system. Or finally, you'll get an identity, which reveals an infinite number of solutions, and that's our consistent and dependent system.
So, the real takeaway here isn't just about finding X, Y, and Z. This four-step process, it does more than just give you an answer. It's really a method of interrogation. It forces a system of equations to reveal its true nature. Every system tells a story. The only question is, what will the next one you investigate reveal?